Welcome back to another class. So today we'll be looking at projectiles. Alright, the projectile motion is a kind of motion experienced by any object projected into the gravitational field. The force of gravity acting on it to pull it to the ground gives it a parabolic shape. So once an object is thrown into the air, it has this parabolic kind of motion, and that's because the force with which you threw it into the air propels it in the horizontal direction, but then the force of gravity pulls it vertically. So you're going to have your force thriving in the horizontal direction and the force of gravity thriving in the vertical. So that makes the object move in a parabolic path. All right, and that kind of motion is what we call the projectile motion. So examples of this kind of motion include a boy shooting a stone at a bird with his catapult. So a bullet fired from a gun, an athlete using a diving board, a thrown javelin. All those are kind of projectile motion where you have the object move in a parabolic path. The projectile is subject to two independent motions. One, the horizontal motion, and two, the vertical motion. Like I said earlier, the horizontal motion is propagated by the force with which you throw it. While the vertical motion is propagated by the force of gravity on it. So this is a pictorial example of what we're talking about. So you can see if this object is in space moving, it's going to experience both forces. The force with which it was thrown that propels it in this direction. So that's if we're saying it was thrown in this direction. So it's going to experience this horizontal motion, moving in this direction, and then a vertical pull of gravity. So instead of it to just move on straight like this, it's going to find itself moving in a parabolic path. Moving in a horizontal direction, but as well moving in the vertical direction. And so we're going to eventually have this object around here. Alright, so this is another one with which we assume the object is thrown from the ground and it goes to a maximum height and drops back to the level with which it was projected. Alright, so if we have this object at any of these points, any point along this parabolic path, wherever you find the object along the parabolic path, it's going to have the horizontal component and the vertical component, which is represented here with this very transparent object. So we have the horizontal component, we have the vertical component of its motion. We have the horizontal here, the vertical here, we have the vertical here, we have the horizontal, we have the vertical, the horizontal, the vertical, the horizontal. Alright, so the horizontal component of the velocity, Vx. Remember, we use V to represent the final velocity, while U to represent the initial velocity. So that's why we have U at this point and V at this point. But here we're saying the horizontal component of the velocity, Vx, at any point on this parabolic path, the horizontal component will be U cos theta, which is the initial velocity cos theta. So if we say we're looking for the velocity of this object at this point, with reference to its initial velocity, of course, it's going to be U cos theta. We're going to find the angle it makes with the x-axis, alright, and then find the cos of that angle and multiply it by the initial velocity. That will give us the horizontal component, which is this component, that is the velocity with which it moves in this direction. Now, the vertical component of the velocity is going to be Vy equal to U sine theta. Alright, so to find the vertical component of the velocity at any point, we have to get the sine of the angle it makes with the x-axis and multiply it by the initial velocity. And we're going to get that component, right, in the y direction. Of course, in this case, in the y direction, it is moving upwards, because obviously it was thrown by a force, and that force obviously was greater than the force of gravity, so it had to move upwards. But then the force of gravity is acting on it still to reduce its velocity in the vertical direction until it comes to a point where it is still where it is still vertically. It doesn't move, it's not moving upward or downward. Then once it crosses that point, the force of gravity wins and it starts coming down. So now we have a vertical component pointing downwards. Alright, So the horizontal component of the velocity is assumed to remain constant, as the force acting to resist motion is also assumed insignificant and can be ignored for now. But the vertical component is altered by gravity tangibly. Okay, so we are assuming our horizontal component remains constant. Okay, and that there are no forces opposing it. Okay, even if we know that definitely for an object flying in the air, we could have air resistance, we could have other factors that would oppose that motion, but we're assuming those factors are negligible. Okay, so we can really consider what's really important for our consideration in this course. Okay, so for that reason, since the object is altered by gravity greatly, we have a way of applying formulas to get accurate answers. All right, so whenever we have the object ascending, remember here I showed you that once the object is going up, the force with which you shot it upwards wins. Okay, it defeats gravity, and so the object floats upwards, all right, until the point where gravity wins. So in this case, your vertical component is pointing upwards, and in that case, when we're applying the formula for finding velocity, okay, we are going to be using the negative, all right, for ascending. Let's remember that this formula is gotten from one of the three laws of motion, which is v equal to u plus at. Then we now also talked about gravity. When we're using the formula with respect to gravity, we now have v equal to u plus or minus gt. Okay, so in this case, it's going to be negative when the object is moving upwards and positive when the object is moving downwards. And that's because the velocity here for the vertical component is the initial velocity sine theta. That's the vertical component minus the force of gravity. Okay, while when it's coming down, you have that same component plus the force of gravity, because now the force of gravity is acting to pull it down, in addition to the vertical component of the velocity. Okay, having said that, there are important parameters of the projectile that we will be considering, and they are time of flight, maximum height, and range. Okay, so we're going to try to derive them from the equations of motion. They are obviously very simple derivations, and we will see how we can apply them to solve problems of projectile motion. The height at any time of a projectile flight is determined by s equal to ut plus or minus half gt squared. I'm sure you remember this formula from the three laws of motion. Now, if we have to use this formula, then our s here will represent the vertical height. Remember, we have the height attained, so we're considering the vertical distance from the plane of projection. Okay, so s will represent that height, u will represent our initial velocity, g will represent gravity, and t will represent time. Okay, so if we write this formula in a way to suit our narrative, we'll be having y equal to u sine theta. All right, now this u in this formula represents initial velocity, but now in our case it's going to represent the vertical component of the initial velocity. Okay, because our initial velocity has a vertical component and a horizontal component. Okay, because this object is moving in both directions. It's moving both in the x-axis and the y-axis, and the velocity is experienced in both directions. And so we have to split the velocity into these two components to be able to understand the motion properly. All right, so y is equal to u sine theta, because in this case we're considering the vertical component of the velocity. Okay, times t plus or minus half gt squared. Now, time of flight is the time with which the projectile returns to the same level it was projected. Okay, so if you remember from the previous picture that was shown, the object was projected from a plane. Okay, once the object goes through its period of flight and comes back to that plane, okay, the time with which it goes through that flight is what we call the time of flight. All right, so in the above equation, if we replace t, okay, with the time of flight, because obviously t here represents time, so since we're looking for the time of flight, and we want to use this equation, we can replace t to be that time of flight. So if we're considering the time of flight, what do you think our y will be at the end of the flight? At the end of the flight, obviously our y is going to be 0, because y is the distance, okay, the object has from the plane of projection. And after the flight, remember we say that the end of the flight is when the object comes back to that plane of projection. So y automatically is 0 because the object is back to the plane of projection. Alright, so y is equal to 0 since after flight vertical distance is equal to 0. So we're going to have 0 equal to u sine theta times time of flight minus half g time of flight squared. Rearranging this, we have half gt squared divided by t. Okay, rearranging this, we take this to this other side, so we have half gt squared equal to u sine theta times time of flight. Now if you divide both sides by time of flight, okay, so we're trying to make t the subject of formula. If you do that, we're going to have finally t equal to 2u sine theta over g. Okay, and that's because this t here will cancel this t here. Okay, they would divide themselves out, while this t here would cancel one of the t's here, so they would definitely divide themselves out. So t would then be automatically equal to u sine theta, right, all over g, and then multiplied by these 2. Of course, this is half, so if we bring half down here, it's simple as saying u sine theta over g, okay, times 2 over 1, okay, because this is divided by 1 over 2. So once we simplify all that, this is what we eventually get as a formula for the time of flight. An easier alternative to deriving the time of flight is to derive it from the first equation of motion, which is v equal to u plus or minus gt. Considering the vertical velocity at maximum height, of course v is equal to 0. Now what do we mean by this? So let's say we have an object that goes through, okay, this is not very perfect, but I'm trying to see if I can use it to explain what we mean here. So let's say we have an object here, probably a ball, okay, and it goes through this parabolic path and comes back here. All right, now the vertical velocity at the maximum height, which is somewhere here, so this is the maximum height, the distance between the highest height and the plane from which it was projected. Now this is the plane of projection. Okay, the object moves in this path until it gets to a maximum point, and then it starts coming down. So the maximum height is this distance here. All right, now at the maximum height, once it gets to the maximum height, the velocity there is 0. So that's what we're trying to say with this statement. The velocity at this height is 0. Okay, so if we consider that to be the case, all right, then we would have this formula as 0 equal to u sine theta minus gt. Okay, all right, then simplifying this, we have gt equal to u sine theta, okay, which eventually gives us t equal to u sine theta over g. Now this represents the first half of flight. The first half of flight, we're talking about from here to here. This is the first half of flight. We have this other half. Okay, so an easy way to get that half would just be to multiply it by 2, because it's the same kind of motion on the other half. Okay, so we multiply our equation by 2 and we get same formula we got from the previous slide, 2u times sine theta over g as time of flight. So this is another way to derive the formula, and it's easier. Okay, so let's look at maximum height. Maximum height is the highest vertical distance away from the horizontal. Okay, so when we say horizontal here, we mean the plane of projection. Okay, so it's the distance, the vertical distance from the plane of projection to the maximum height the object hits, okay, before coming down. All right, so if you consider this other equation of motion, v squared equal to u squared plus or minus 2gh, okay, and we take our vy to be u sine theta, which is normal, and our v to be 0, okay, because we're considering maximum height, and the velocity at maximum height is 0. Okay, so if we make these considerations, we're going to be having 0 squared, okay, equal to u sine theta squared minus 2gh. Now u sine theta, remember, is the vertical component of the velocity, while 0 here is coming from the fact that the velocity at the highest vertical distance is 0, because the object moves up to that point and stops for a while, for a split second, stops for a split microseconds before it starts coming down. Okay, so velocity at that point is 0, and if we consider that, then we're going to be having 2gh taking this over to the right hand side. 2dh equal to u sine theta squared, which then gives us our maximum height as u squared sine squared theta all over 2g. Okay, making h the subject of formula here. And this is u squared sine squared theta, obviously same as u sine theta all squared, because of course this is u squared times sine squared theta. So let's consider range. Range is the horizontal distance covered by the projectile through flight. All right, so remember, if we have object that goes through this, okay, parabolic path, and we have this plane of projection, okay, our range in this case is the distance from this point to this point. Okay, so the distance from this point to this point would give us our range. Okay, so that's the horizontal distance from the point of projection to the point of landing back on the plane of projection. All right, so that's the horizontal distance covered by the projectile through flight. Okay, so this is our range. Okay, so if we consider that distance is equal to speed times time, then range can be gotten as u cos theta times t, where t will represent time of flight and speed represents the, of course, the horizontal component of the velocity. Okay, so range will be horizontal component of velocity times time at that given point. Okay, so u cos theta will give us times 2u sin theta over g, because t represents the time of flight. Okay, at that particular time, t represents the time of flight because the time at that particular time is equivalent to the time of flight because flight has been concluded and done with. So our range, the time that we will consider for our range will be the time it took it to complete the full flight. Okay, so we have the formula for time of flight representing t. If we simplify this, we're going to have 2u squared cos theta sin theta. All right, okay, over g. So, and we know from trigonometry that 2 sin theta cos theta is sin 2 theta. So that simplifies to give us u squared sin 2 theta over g. The sine of an angle is maximum at 90 degrees. Of course, if you have sine, any angle, if you have sine theta and theta is 90 degrees, then that is the maximum angle you can get from a sine. Okay, and it means therefore that since we have sine 2 theta here, if theta is 45 degrees, then we have the maximum angle we can get from this range. So it therefore means that arrow max is going to be equal to this u squared over g, because once we put in 45 here, sine 2 times 45, which becomes sine 90, would give us 1. Okay, and that's as the maximum angle. So the maximum range we can get, we would get if we make our throw at 45 degrees. Okay, once we do that, make our throw at 45 degrees, we're going to get the maximum range possible for that force that was applied.